Vaishnav College and founder trustee of Pi Mathematics Association. Our dynamic secretary, Mr. Mahadevan. I think the principal of Bala Vidya Mandir is expected to come and join us. And Madam Janata, pride members of AMTI, members of teaching fraternity and my dear students, very good evening to every one of you. Being the coordinator of Popular Lecture Series AMTI, I welcome each one of you on behalf of AMTI and Bala Vidya Mandir for today's talk by Mr. Sivaraman on conjectures and proofs. Dear Mr. Sivaraman, we look forward to listen to your lecture on conjectures and widen our horizon of knowledge. I once again welcome the speaker and the audience for today's seminar on conjectures and proofs. Thank you. The Pi Mathematics Association intends teaching mathematics in an enjoyable manner and making students know that mathematics is indeed a subject which is very essential in our day-to-day life. The main objectives of the trust are to remove mathphobia and make mathematics reachable to students and other professionals alike, to help the deserving students who wish to pursue their higher studies, thereby shaping their future and making them responsible citizens. I now request Dr. Sivaraman to deliver the lecture.
Good evening, one and all. My topic of today's lecture is conjectures and proofs in mathematics. The term conjecture in mathematics is a statement whose validity or truth is not known in certain, at least at the first sight. So we all can make some statements whose proof may not be immediately known to us. But after some time, in some cases, it might happen that it might turn to be false. As some examples of this kind, I can just start giving as introduction to you. See, the number 31 is prime number, isn't it? What's a prime number? Yes, sir. Prime number is the one which has exactly two divisors, namely 1 and the number itself, isn't it? Now, you can have lots of conjectures on prime numbers, and I'm happy that I'm delivering the 11th talk, and incidentally 11 is prime number. So I'm delivering the prime talk today. So the point is, I have given the introduction for the conjecture. Next slide. Conjecture, as I said, was a statement whose truth is not immediately known, but in some cases it might turn to be false. Now, just as an example to you, you take the number 31. 31 is prime number, isn't it? You just add 3 to the left side. So 31 is prime, 331. Just adjoining 3 to the left side. That is prime. 3331. Add one more 3. That is also prime. You add one more 3. That is also prime. Add one more 3. That is also prime. So keep on adjoining 3. You, right from starting with 31, you get sequence of prime numbers. 31 is prime. Is that visible to you? 31, 331, 3331, 3334, 3 and 1, 1. So if you keep on adjoining 3 to the left of 1, each time you always end with prime numbers. Now some might just tend to believe that this pattern continues on and on. So we might just make a conjecture that this sequence will always generate prime numbers. But after 6 terms of the sequence, the 7th number will be a non-prime number. So the conjecture gets broken down. So there are two possibilities of making a conjecture. If you can prove the conjecture, it becomes ultimately a theorem. And if you disprove the conjecture, you have to provide for that disprove a case of an example that in mathematics is called a counter-example. To disprove a conjecture, you need to have a concrete example of saying how the statement is false. And such an example used to disprove the statement is called a counter-example. Okay? So that's the definition of the conjecture that I have given to you. And remember, making a conjecture is not an easy job. Now, particularly making good conjecture is a very difficult task, and centuries have been able to make beautiful conjectures. Because some conjectures, as I just said now, will break immediately the moment after it was reaching to the public. So to break conjecture, even if it is a good conjecture, the falsity may not be known at the first instant. It might even take centuries or even millennia to break. But there are conjectures which stood all times and efforts of great mathematicians, and that. So now I am going to list out the best possible conjectures in mathematics. So I had decided my talk in three categories. The first category of conjectures that I described here was set of conjectures which was not proved yet so far after it was proposed. Normally the conjectures were given titles, the name for the conjectures were named after the corresponding proposal. Okay? Now the most important conjecture, as I felt, and very famous conjecture among all, is Goldbach conjecture. That is the first conjecture, Goldbach conjecture. Now, there was a mathematician called Christian Goldbach who lived in the 18th century, and he was corresponding to the greatest mathematician of all times, called Euler at that time. And in one of his letters in 1742, he wrote to Euler that he had two conjectures with him, believing that every even number greater than 2 is always sum of 2 primes. This is his first conjecture. Now, if you take 4 is an even number after 2, 4 can be written as 2 plus 2. Those two are prime numbers. If you take 6 can be written as 3 plus 3. What is 8? 3 plus 5. Both 3 and 5 are prime numbers. What is 10? 5 plus 5 or 3 plus 7, whichever way you write. In either case, you have written 10 as sum of 2 prime numbers, namely 5, 5 or 3, 7. What is 12? 5 plus 7. 5 and 7 are prime numbers. 14 is 7 plus 7 or 3 plus 11. In either case, you get 2 prime numbers. So Goldbach actually viewed this property and he mentioned that he couldn't prove this result. And it remains even an open problem today. That conjecture has not been proved till today. So it has been standing for nearly 160 years, more than 160 years. The second conjecture, the same letter to Euler, states that every odd number greater than or equal to 5 can be written as sum of 3 primes. Every odd number strictly greater than 5 can be written as sum of 3 primes. For example, take 7. 7 is 2 plus 2 plus 3, and 2, 2, 3 are prime numbers. Okay? And what is 9? How could you write 9 as sum of 3 primes? Just think. I have written there 9 is, write 9 is sum of primes. 2 plus 2 plus 5. Okay, so 9 is 2 plus 2 plus 5. So every odd number greater than 5 can be written as sum of 3 primes. But this conjecture by Goldbach was called weak conjecture, and the first conjecture that I mentioned was called strong conjecture. This is called weak conjecture because the proof of the second conjecture partly was proved by a Russian mathematician in 1854 called Vinogradov. He made a very vital breakthrough in 1854 by proving that for some huge number, some huge odd number, say capital N, at a certain stage, every odd number can be written as sum of 3 primes. But unfortunately, that stage that he was talking about in his proof was so huge. It is up to like 3 to the power 4. So it's very huge number. So you can't start the proof by within beginning numbers, as I mentioned, for 7 or 9 or 11. So that proof was only at a certain stage, not from the immediate stage. And therefore, that proof, though it was admitted to be one of possible proof of second conjecture, but it's not whole part of the proving, and mathematicians now are trying to gap out or swallow that stage in the proof. My second conjecture to you was called Levy's conjecture, which is somewhat similar to Goldbach's conjecture. Can you see the odd numbers greater than, what is it? Greater than or equal to 7 is written as sum of prime and 2 times another prime. This is very similar to Goldbach's conjecture, but here you write the number as sum of prime and 2 times another prime. So I have listed out all the possibilities. For example, 7 is 3 plus 2 times 2. Okay, so 3 is prime, 2 is prime. 9 is 5 plus 2 times 2. 5 and 2 are prime numbers. So here we say that every odd number greater than or equal to 7 is written as sum of an odd number plus sum of prime plus 2 times other prime. Those two numbers are prime numbers. So this is called Lewis conjecture. Again, those proof or disproof is not known till today. No one knew the proof. The next conjecture is called Polygnac's conjecture. This man was very famous in making conjectures in our field, this D. Polygnach. Now he, in 1849, conjectured that for every even number 2k there is prime. But this result was very great result. The conjecture was very great conjecture. In the sense that we call some numbers as twin primes, we call some numbers as cousin primes, we call some numbers of different names. There are more than 50 types of prime numbers. And I was talking about primes initially. See, two prime numbers are said to be twin primes if they differ by 2 from each other. Like 3 and 5 are twin primes. Because the difference between 3 and 5 is what? 2. So in general, twin primes are numbers of the form p, p plus 2, where both p and p plus 2 are prime numbers. So the difference between the prime numbers is 2, they are called twin primes. Is that clear? So 3, 5, 5, 7, is that clear? 11, 13 are twin primes. 11 and 13, that's a twin prime. Now this conjecture says that for every even number, say if you take 2, k is 1 here, you get 2k as 2. You get all infinitely many twin primes. If you take k is 2, 4, then you get gap of 4 numbers. I mean, if 2 primes are said to be cousin primes if they differ by 4. 2 primes are said to be sexy primes if they differ by 6 between them. So Polygnach conjecture that between every gap of even numbers, 2, 4, 6, 8, 10, 12, you can have infinitely set of prime numbers. Like you can find infinitely prime numbers for the form p, p plus 2, p, p plus 4, p, p plus 6, p, p plus 8, p, p plus 10. So, and there was wonderful result. In particular, the primes of the form p, p plus 2 is very famous in mathematics for twin prime conjecture. Again, that is not known to be true till today. One of very old conjecture. Anti-cross conjecture is related to, again, viewing the gaps between prime numbers. See, prime numbers are so mysterious objects in mathematics. The point is there is no explicit formula for writing down the given set of prime numbers. People are trying to locate such an idea, but I am talking about distribution of prime numbers in conjecture in my later slide. So I'll explain that. This conjecture simply says if Pn is n prime, Pn plus 1 is n plus first prime, the root of Pn plus 1 minus root of Pn is strictly less than 1. What does it say? So supposing, what is first prime number? What is first prime number? 2. What is second prime number? 3. So this says that root 3 minus root 2. What is root 3 minus root 2? Root 3 is approximately 1.73. And root 2 is approximately 1.4. Subtracting this, you get 0 point something, 0.4 or 0.3 something, which is strictly less than 1. And if you take 3 and 5, the next two prime numbers, what is root 5 minus root 3? Root 5 is 2.236 approximately, root 3 is 1.732. So subtracting you get around 0.6 or something. That is again strictly less than 1. So if you keep on taking two consecutive prime numbers, say Pn and Pn plus 1, like 5, 7, 7, 11, 11, 13, and if you just subtract their square root, the differences will always be less. So this is for anti-cross conjecture. And the largest gap of that value occurs for root 11 minus root 7. This was tested up to 1 lakh prime numbers. The largest difference occurs in the case when you take root 11 and root 7. So root 11 minus root 7 is the maximum value of the difference. And the next conjecture is called Beckmann's conjecture, which is again involving like geometric series. Beckmann conjecture that is the only equation in primes, like 1 plus 2 squared, etc. over root to the power 12 is equal to 1 plus 5 plus 5 squared. 1 plus 5 plus 5 squared. Now, Bateman conjecture that this is the only equation that you can have for powers of prime, adding consecutive powers of prime, and no other equation exists. And this remains even today unproved state. That is also a conjecture. No one knew the proof of it. But if you allow the equations to have opposite numbers, which are opposite numbers or non-prime numbers, you can have at least a couple of solutions, and that is one of the possible solutions. And this next conjecture was called Bean's conjecture, and it was offering a phrase, so I included that phrase here. Now, Bean was not a mathematician, he was a banker, in the sense he was so rich in America, and he used to fund for rocket launches, NASA agencies, and he wanted to use his money in a constructive manner. And he was a great influential man, one of the great men in America. And he wanted to, when he was just investigating with his computer at spare time, he found that if you take the equation x power m plus y power n, this is z power r, then m and r are positive integers, x, y, z are positive integers, the x power m plus y to the power n is equal to z to the power r. M and r are equal or may not be different, but both all the integers should be greater than 2. All the integers should be greater than 2. What happens if m and r are each 2? What will happen if all the powers m and r are 2 each? You get an equation like x squared plus y squared is equal to z squared. And that is your famous Pythagoras theorem. Now, there are infinitely many triples x, y, z for which x squared plus y squared is z squared. There are so many formulas. Now, what Bean observed was within his power of computation and with his computers, that if you allow the powers to be greater than 2, like m and r, not everything equal to each other, and if you allow the power to be greater than 2, then we found that the solutions that x, y, z were we possessed always had a common factor between them. That is, x, y, z always have GCD, which is greater than 1. The GCD of x, y, z is not 1. All x, y, z are multiples of some particular number. They are not co-prime. So that is what he observed, and he checked this result in his computer for many cases, as long as 1 lakh powers, and he could not get any case where the numbers x, y, z are relatively prime to each other. Therefore, he made this conjecture, and in fact offered a prize for proving or proving this conjecture, and till date it has not been proved or disproved. It remains as a conjecture. As offering, he initiated $5,000 for proving or disproving this particular result for the man who just find this, and he subsequently increased every year by $5,000. So that the proof comes in second year of this. He made his conjecture in 1987. So if someone could prove that in the second year, it will be of $10,000, and third year it is $15,000, with a maximum of $50,000. And he used that interest. No one claimed the price because no one gave the proof of this conjecture. Therefore, the price remained intact in his bank, and the interest that was obtainable through this price amount was used to fund what is called Andrew's Memorial Lecture, one of the great mathematicians. Now, my next conjecture to you is what is called Catalan's-Mersenne conjecture. Now, here, I wanted to just say that Mersenne is a monk who lived around 17th century AD, and was very much instrumental in modern development of mathematics. He is not, by profession, he is not a mathematician. He is just a monk who works for prayer purpose in some churches. He is just like a father there. But he, because of his passion that he had in mathematics subject, he was just corresponding with all the leading mathematicians at his time, including Euler, Fermat, Pascal, Descartes, everyone. He was just corresponding to them. And he urged them to work on great problems. Because you know that there was no internet or email facilities, or there was no STD connections at those times. So that you can't just send your ideas immediately to each other in different parts of the globe. Therefore, they need some propagator to do this work, and Mersenne, the French monk, exactly acted as just like a postman corresponding between two great peoples at that time. And he was very much instrumental, and I can say this information to you that the largest crime that is discovered today, in today's time, were called Massine crimes. It was called in this name called Massine crimes. So Massine was, Massine crime is the number of the form 2 power p minus 1. 2 to the power p minus 1 whenever p is prime. For example, 2 is prime, isn't it? So what is 2 squared minus 1? 3. 2 squared minus 1, 2 to the power 2 minus 1 is 3. That is the Massine prime. 3 is prime. What is 2 to the power 3 minus 1? 2 power 3 is 7. 2 power 3 is 8. 8 minus 1 is 7. So such numbers 3, 7, 31, 2 power 5 minus 1 are called Massine primes. Okay. Now 17 is not Massine prime. 17 cannot be written as 2 power something minus 1. Okay. So all primes are not Massine primes. Okay. You know that the largest prime that is existing today is the largest Massine prime is 2 to the power 43,112,609 minus 1. And it has more than 14 lakh digits. That is the current record for largest prime. Okay. And my last one is that Canon's problem. I haven't mentioned it previous time. The term Caron, he was a French mathematician again, and he was doing great works in number theory. And he, along with Massine, because he used the idea of Massine. Now I was telling you that Massine primes are two numbers of the form 2 power p minus 1 whenever p is prime. Now he was observing that 2 to the power 127 minus 1 is prime. But that 127 itself is 2 to the power 7 minus 1. So what Catalan observed was, he defined sequence of numbers like C1, C2, C3, C4, C for Catalan. C1 is 2 to the power C0 minus 1. The C0 is first Massine prime. What is first Massine prime? 3. So the answer is 3. What is C2? 2 power C1 minus 1. What is C1 there? 3. So 2 power 3 minus 1, that is 7. And what is C3? 2 to the power C2 minus 1. 2 to the power previous answer minus 1. 2 to the power previous answer minus 1. So surprisingly, the answer in each case turns out to be prime numbers, and such numbers are called Catalan or
Is there any connections between this and we have definition for the Catalan? I think very good.
Yeah, there is a connection. Yes. So yes, but the point is, if you go to the fourth stage, that answer, that number, it is again prime number. But if you go to the next stage, that the number is so big that it is having nearly 10 to the power 38 digits. It's too long to verify even whether the number is prime or not. So it still remains a contention. No one knew whether the sequence produces all prime numbers. Now, this is the most important conjecture among all conjectures. The point is, every mathematician, whole big mathematician existing today, just dream of proving this result. It's called the Riemann hypothesis. One of the most secret unsolved problem in mathematics. If you go and ask any seasoned great mathematician working in any branch of mathematics, and you just put a question to him, what problem that attracts you more to solve with, he immediately tells you that the problem is invariably Riemann hypothesis. Now, Riemann hypothesis, why that is so important? See, I have been telling you some Bateman's conjecture, Bean's conjecture, Catalan's conjecture. Those are conjectures which are beautiful in mathematical ways in explaining to mathematics, but they don't have much deeper applications. The sense, only few, not many. But the Riemann hypothesis is the one for which you have plenty number of applications. But there are so many theorems that depends on the truth of Riemann hypothesis. So in the sense, if one could prove Riemann hypothesis to be true, then all the other set of results which depends on Riemann hypothesis will immediately fall. Those results will also be true. And as far as I know, there are more than 100 theorems which depends on Riemann hypothesis. Not one or two, more than 100 theorems, great theorems, depending on the truth of Riemann hypothesis. And it was proposed by the great German mathematician Riemann in one of his wonderful papers. He published in Berlin Academy in 1859. He was working at Göttingen University, and that paper was just 8 pages problem. So the 8 pages paper created a problem which is even unsolved today. So it's been now 150 years, the 150th year of proposing of Riemann hypothesis. So, as I mentioned, the problem became interested in many ways. One way of interest is because most of the other theorems or results depends on Riemann hypothesis. So, if one happens to prove the Riemann hypothesis to be true, then other results will also be true. And the other hand, if Riemann hypothesis seem to be false, then there are other set of results which depends on falsity of Riemann hypothesis. That is the beauty here. So everything will get stopped. It's just like arranging a pack of cards one after the other. If you pull up one card, everything will go. Just follow. Even plugging one card out of building of cards, even if you just plug one card, everything will go. So that is breaking the conjunction. But no one knew even today. Now the Riemann hypothesis is all about, because it's the best unsolved problem in all of mathematics today, the greatest unsolved problem in mathematics today, and it depends on the arrangement or distribution of prime numbers. Riemann hypothesis talks about the arrangement or distribution of prime numbers, how prime numbers are distributed. I will be talking about one other theorem which is very similar to this, but somewhat lesser in concept than Riemann hypothesis. That is called prime number theorem. Now, Riemann hypothesis answers several questions, and if you can prove Riemann hypothesis, you can find a structure or pattern of the behavior of prime numbers, and that is one of the holy grail of mathematics. Because as I mentioned earlier, no one knew how prime numbers are distributed in real life, and such a distribution is so mysterious to all great minds so far. And if someone has to prove Riemann hypothesis, they will in fact definitely create a great breakthrough in mathematics history, and they become world famous, no doubt about it. And moreover, Clay Mathematical Institute in America has instituted some awards. In 2000 May in France, Clay Mathematical Institute included 7 unsolved problems, and Riemann hypothesis for the first among them. Okay? They included 7 unsolved problems. They call such problems as millennium problems. And those who can prove or disprove all these problems or conjectures, including Riemann hypothesis, will be awarded a prize money of $1 million US. So not only that you can get fame throughout the world, you can be rich also. So these conjectures are so important in many aspects. It will make you rich on the day. And the point of the other historical background about Riemann hypothesis is that it was only the unsolved problem left out in the Hilbert's list of 23 problems. There was a German mathematician called David Hilbert who announced 23 important problems in all branches of mathematics in ICM, International Congress of Mathematicians, held at 1900 in France. Now he announced that he collected very instrumental and vital problems in all branches of mathematics, and he posed 23 such problems. And he believed that most of the problems, at least more than 10 problems or 23 problems, will never be solved in recent centuries. He never thought that way. But to his surprise, most of the problems within 10 years of his announcement get solved immediately, one after the other. And this is the 8th problem. Riemann hypothesis was the 8th problem among those 23 problems that Hilbert proposed. And I can say that when we entered millennium, 2000, exactly 100 years after the announcement of such problems, this is the only answer. All the remaining 22 problems were eventually solved by mathematicians of that particular century, and Riemann hypothesis was the only problem that remained unsolved from Hilbert's original list of the 3 problems. And that is why I took an 8th conjecture. That this problem was originally 8th problem in Hilbert's set of problems. And it carries a more historical, sentimental, because it answers more than anything else in mathematics. I mean, it was a dream for every budding mathematician or even a great mathematician, even today, that their dream was to just prove Riemann hypothesis. You might be knowing about Hardy, the mathematician who helped Ramanujan in revealing his genius. Hardy loved Riemann hypothesis like anything else in his life, and in one of the 6 wishes that he proposed, he ultimately wished that he wanted to prove Riemann hypothesis. And in fact, he nearly proved 50% of Riemann hypothesis. Hardy proved nearly 50%, but not the whole part. So Hardy was instrumental in proving some part of Riemann hypothesis, but not everything. Even Ramanujan tried proving Riemann hypothesis, but it went in vain. He couldn't prove it. So it was one of the great unsolved problems no one knew. It just says that it talks about what is called zeros of the zeta function. Yes, I do not know how you study complex numbers. Complex numbers, do you know complex numbers? Yes. A complex number will be a number of the form a plus ib, where a, b or real numbers. Now, the Riemann hypothesis just says that the zeros of the zeta function, Riemann zeta function, all non-trivial zeros will have real part always half. So if you draw the graph, you see that half is a line parallel to y-axis. So all the non-trivial zeros of zeta function will align mysteriously in the vertical line parallel to y-axis and distance half unit. And Riemann himself gave a wonderful formula for computing first few zeros. And Riemann hypothesis claim was verified to high computers now. And they checked that the hypothesis is true up to 3 billion zeros. They computed more than 3 billion zeros now. And none of the zero went out of this line. It always stick on that line. So most of the mathematicians today believe that it could be true. But anyway, no one knew how it was true. So far I have been listing out conjectures for which the truth or falsity is not known completely to us. In some cases, some of the results are known, but not yet completely. One of the conjectures that I mentioned so far were proved. So far not disproved, nothing is known. Now, the second category of conjectures in the lecture is that those ideas that I am going to mention now were great unsolved problems at previous stages, but they remain proved. They are subsequently proved by later mathematicians. So this is a set of conjectures whose proof is known to us, in other words. Okay? And one among such conjectures is undoubtedly Fermat's last theorem. And there is a wonderful book about this by Simon Singh, who directed Fermat's last theorem documentary. He wrote a wonderful book about it. Those who want to know about Fermat's last theorem can just pick that book and know everything about it. Now, Fermat's last theorem says that if you take an equation of the form x to the power n plus y to the power n is equal to z to the power n, then it doesn't have any solutions in natural numbers when n is either 3 or more than 3. And again, if n is 2, you have Pythagoras theorem. X squared plus y squared is z squared. Now, if n is more than 2, like 3 or 4 or 5 or 6 or higher powers, you don't have any solution. The remarkable aspect about this particular theorem is that it could be understood by everyone. For example, when I told about Riemann hypothesis, most of you could not feel comfortable in knowing what it is. It's very difficult to explain. That the explanation of what Riemann hypothesis itself is a 2-hour lecture. That itself can be explained in a whole lecture. What is Riemann hypothesis? That itself can be explained in a whole part of the lecture. So even to introduce what it is, it takes more time for us. Such a way the conjecture is so deep. But here the conjecture is so simple that even a high school student can immediately grasp and immediately guess what it is about. That is the most interesting part in Fermat's last theorem. Fermat, the amateur French mathematician who was basically a lawyer in French courts, was using his spare time to just scribble in Diophantus Alexandria book, and he was scribbling his observations in the margins of those notebooks. And this was the most famous theorem until the most famous conjecture until it got proved in the year 1995. Now there was so much of mathematicians who just wanted to try to prove this. It was proposed in the year 1637 by Fermat. And it was known to the world only by 1670 after his death, not immediately. This theorem was known only in 1670 after 5 years of his death, and it was published by his son. Okay. And right from the moment of its publication, mathematicians like Euler, Gauss, most famous mathematicians of all times were devoting their energy to prove this. Because Euler made great breakthroughs in Fermat's last theorem. He proved that there is no solution for n is 4, 5, and certain lengths. And there was one mathematician called Kummer who proved that it won't work for regular primes. The results prove whenever n is a Sophie Germain from Germany, who produced a wonderful idea for proving this result. That was one of the breakthroughs in proving this theorem. But I'm very much sure that the proof involves so many pages of heavy duty mathematics. It was not an easy proof. It was proved ultimately by Andrew Weiss of Princeton University. And have the video, there's a wonderful video about that last year, depicting how the conjecture was made, how eventually how many breakthroughs were made in the middle period of time, and how it was solved. And you can see the documentary was spoken taken directly by the man who proved that Andrew Weiss. It was very emotional moment for him when he got into it. Now, Andrew Weiss actually was a very influential mathematician at Princeton University who dreamt of proving this right from the age of 10 when he saw this theorem. He saw this statement at the age of 10. He was born in 1943. He saw this probably in 1953 in his library. The moment he saw this, he had an urge in him of proving this. And most part of the thing that, very fortunately, his research area was for elliptic functions. And he used that elliptic function theory to do this, and I can say that there are 4 or 5 most important ideas like elliptic functions, modular forms, Galois representations, and all those ideas, most part of beautiful connections existing between all branches of mathematics exist, and the proof is more than 300 pages long, not a few pages. So it was, they gave this lecture for more than 10 days. And he gave the proof on 23rd June 1983 at Isaac Newton Institute in England. And everyone believed, the news flashed everywhere that great Fermat's theorem was proved. And again, there were so many prizes that were offered for proving this. He was ultimately offered all those prizes. But before doing that, see, when you publish something, it has to be refereed. When I want to put a paper in mathematics, I just come up with an idea. My paper, how to judge that the results are correct. It should be refereed by some expert in this relevant field. And that proof was refereed by his source Nick Katz. And he was referring one by one each page of the proof. The proof is very long. So it took months to referee, 2 or 3 months to referee. And each time when he had a doubt, he called Andrew Weiss and just spoke to him. I had a doubt here. Just explain me how to arrive at this test and all those things. And he used to clear all the doubts subsequently. But one point of time, Nick Katz felt that there was a very serious gap in the proof of Fermat's last theory. And when he contacted Andrew Weiss was not in a position to explain to him. He admitted that his proof was wrong. And that was a great moment of defeat for him. And he became so sad that he never spoke to anyone, he never ate for some days. And until he made it right, he was not in his usual position. For proving this theorem, he cut short all his worldly activities. He never attended any function. He never went anywhere. He spent nearly 8 years for proving this. He never did anything else apart from attacking these proofs. That is the energy that they had spent in proving this results. Subsequently, by God's grace, with this student called Richard Taylor, who helped him cracking this proof, and they subsequently got the right proof in the year 1995. It took nearly 1.5 years for even cracking the proof. So, one of the best ideas in mathematics. The next conjecture that was eventually proved, it was known as a conjecture but got proved, was Bertrand's postulate. And I can tell you that Ramanujan in one of his papers has proved Bertrand's postulate in a very elegant manner. Ramanujan has written 30 papers in his lifetime on his own, and in one of such papers he proved Bertrand's postulate in the year 1990. So he claimed that between every number n and twice the number, 2n, there is always a fact. That is Bertrand's postulate, and it seems to be so easy to guess. But eventually the proof came only after a certain number of years, after very hard work. When Bertrand himself has verified this proof for all n up to 3 lakhs, not for 1 or 2 numbers. They are calculating prodigies. They don't stop with the few values of n. But he was very much convinced that there is a general proof for this, but eventually it was proved with Chebyshev, the great Russian mathematician in 1850. But it was again proved with Karl Edish in his age of 21 years, for which he got his PhD. At the age of 21, he proved that Bertrand's postulate, for which he was got his PhD. So, and even Ramanujan proved to say this. So the next issue that I was talk to you about is prime number theorem. It's not as good as a result like Riemann hypothesis, not as strong result, but again it answers how prime numbers are behaving. So just to have a glimpse of what prime number theorem is about. We talk about in mathematics number theory called pi of x. Since pi of x is a function called prime counting function. The sense that it counts number of primes less than x up to that number. So for example, say pi of 10 is 4 because there are 4 primes up to 10. How many primes you get up to 10? 2, 3, 5, 7. Nothing else. So pi of 10 is 4. What is pi of 15? What is pi of 15? 2, 3, 5, 7, 11, 13. So it should be 6. So pi of 15 is 6. So they talk about pi of 10 for every possible end, and Gauss, the great German mathematician, at his 15th year of age, saw some pattern in pi of n comparing with them. In fact, he saw that pi of n is very close to the average n by log n. In other words, pi of x, the number of primes up to the number x, is very close. That answer is very close to the ratio x by log x. And this theorem is called prime number theorem. But Gauss does not prove it here. He could not prove it. And the later mathematicians, after much great effort, it was proved in 1896 by D. Lawson and Jacques Hahnemann. Hahnemann was a great mathematician. So those two mathematicians independently got this, but they used again so much of calculus and heavy duty mathematics to give the proof. And the same theorem was reproved in the year 1949 by two great mathematicians, Paul Ehrlich and Anton Selberg. And that's man Selberg got Fields Medal, the highest recognition for mathematics awards for any mathematician. Now there was a French mathematician called Henri Poincaré, who lived in later part of 20th century. He was a brilliant mathematician, and he actually did great works in differential geometry, what is called algebraic geometry, topology, everything. He was completely all-rounder. And he, in one of his works, he just said, Poincaré conjecture, very simply speaking, because it involves so many technical terms which you couldn't follow. But simply speaking, what he said was, you take any object, like without poles, there's no hole, there should be no hole. You take any object, like it should be having some elasticity, you should bend like this. When you bend it, you should bend like this. You can bend it in any form as you like, because it has some elasticity. Perfectly elastic body. You take anything, like for example, if you take an oval shaped object like what they have in the rugby games and all those things, oval shaped object, if it is elastic, you can bring it, you can compress it on either sides and bring it to a ball shape. And what is ball shape in mathematics called? A sphere. It's technique of three sphere. Now, Poincaré said simply that it doesn't matter whatever object that you take initially. Initially it can be any form. You can rearrange it to the ball form. So every initial object shape which has no holes in it, three-dimensional space, can be put into the ball shape, into three sphere. And that theorem, very loosely speaking, is what Poincaré's conjecture. It seems to be on very first hand, very easy to guess. Well, I can just compress here and there and make it the ball. It's not so easy to do. He made this conjecture in the year 1904, and you see that the proof of Poincaré's conjecture was done only in the year 2004, exactly 100 years after Poincaré's conjecture proposed this conjecture. So it was very influential, and again there are so many results dependent on Poincaré's conjecture. So the moment this was proved, everything else followed from this. And I wanted to just mention a few words about the man who proved this. His name was Grigory Perelman. Grigory Perelman proved Poincaré's conjecture. He was a Russian mathematician, and he got Fields Medal. He was awarded Fields Medal in the year 2006 in the ICM held at Madrid, Spain. Last ICM was held at Madrid from 22nd August to 30th August. Madrid, the capital of Spain. Now here, Perelman was awarded Fields Medal, and it is again one of the millennium problems that I was talking about, almost like Clay Mathematical Institute. There are 7 problems on a speculative mathematical institute. What is Riemann hypothesis? Other one is Poincare conjecture. Other problem is Hodge conjecture. Other problem is P versus NP problem. Other one is Navier-Stokes problem. So I mean there are 7 in number. Right? Okay, so other problems I purposefully rejected here because I thought even the statements or explaining what it is so difficult for you to grasp. So I thought this was quite okay for you. And this was very famous result because, as I said, though there are several conjectures existing in mathematics, only few conjectures were so important because the other results depended on those conjectures. So in that way, this historically is very important. And Perelman rejected the Fields Medal. He rejected the $1 million offer given by J. Mathematics Institute. He never wanted anything. He just said, I wanted to be a mathematician. I'm happy that I proved this. I know that the proof is correct. And it was accepted now by all people. That's enough for him. He left the job at this university and he was just staying with his mother and he was helping some poor students at a village. He never wanted anything, have anything in his lifetime. That was such a great human being. My third category of conjectures, I'll pass it very quickly, is a case where even great mathematicians, just like Fermat was having given Fermat's last year very great result. In fact, Fermat wrote 48 observations in his scribbling of the Alexandria book, in which almost everything comes to be right, excepting few things. Now, the pattern, like just what I mentioned at the beginning of this lecture, the 31, 331, seems to be generating a particular set of things. But after a certain time, or at a certain stage, it gets broken up. That pattern gets broken up completely, it becomes random. So the conjecture gets broken up. So even mathematicians like Fermat had a mistake in that case. Now numbers of the form 2 power n, you can make 2 power n plus 1 are called Fermat numbers. Numbers of the form 2 to the power n plus 1 are called Fermat numbers. So for example, if n is 0, what is 2 to the power 0 plus 1? What is 2 to the power 0 plus 1? 3. Is that fine? Yes. What is 2 to the power 1 plus 1? 5. That is prime. What is 2 to the power 2 plus 1? 17. Should be 17. Is that right? 2 to the power 2 square is 4. 2 to the power 4 is 16 plus 1 17. And if n is 3, you get 2 to the power 3 plus 1, that is 257. That is also prime. And for the next step, if n is 4, you get 2 to the power 4 plus 1, that is 65,537. That is also prime. So Fermat could not compute after this stage, and he just mentioned in his scribbling that all this number, the expression 2 to the power n plus 1 for every whole number n will always give a prime number. He made this conjecture. But Euler came after. Euler was instrumental in proving almost all of Fermat's conjecture, and he subsequently saw that when n is 5, you get 2 to the power 5 plus 1, which is 2 to the power 32 plus 1. And that number has this opposite. He proved that is not prime. A number which is not prime is not opposite. And he proved that 641 divides 2 to the power 32 plus 1 with very ingenious argument, and therefore that is not prime. So Fermat's conjecture was immediately disproved. But Fermat, remember, Fermat was very great in thinking. He's not an ordinary man. He made beautiful theorems, wonderful conjectures. His thinking was so deep into the numbers, that he was mentioned as father of modern number theory. So he's not an ordinary man at all. But this idea escaped from his mind. And this is the scope of mathematics, that I always feel that anyone can come with good conjecture or good way of thinking, and that can baffle even the greatest of all mathematicians of every time. As just an example in this regard, there was one student called Nagini, who was just a 10th class student, who came up with finding the second pair of least pair of amicable numbers. Okay. The first least pair of amicable numbers is 220, 284. That was found as early as in Pythagoras' time. Pythagoras described the first pair of amicable numbers, 220 and 284. See, set of two numbers, A, B are said to be amicable numbers. I don't want to go into detail. If sum of divisors of the first number gives the second number, and vice versa. If you add divisors of all the number 220, all the divisors of 220, you ultimately get 284. But you cannot go 220 itself because any number divides itself. So count all the reversals of 220 excluding itself, you get 284, and count all the reversals of 284 excluding itself, you get back 220. So such numbers are friendly numbers or amicable numbers because they have so much connection between them. And mathematicians extended them to the idea of aliquot cycles. Okay, so they are great things. Now, Fermat deceived by this pattern. So this is my observation in third category. Okay, the next condition that I want to is Polya's condition. You might be knowing that. Have you heard about George Polya? He is one of the mathematicians of the 20th century. He lived for more than 90 years and he was a great mathematician. And he again was deceived by this pattern. He said that if you take number of if you take number of odd integers, number of odd integers less than n with odd number of factors, he believed that it would be always less than number of odd integers having even number of prime factors. So number of integers having odd prime factors is always less than number of odd integers having even number of prime factors. And this was believed to be true because Polya was himself a great established mathematician. And nearly for 40 years no one came with any proof of this. But later, one mathematician called Tanaka came with one counter-example saying that it was false, indeed false. And in fact, Paul Adish later on proved that there could be infinite GP that you can consider for algebraic or not GP for AP that you can find for this theorem can be used. Next conjecture. Next conjecture that I want to tell you is called Carmichael's torsion function conjecture. Now, Carmichael was an American mathematician who gave what is called Carmichael numbers. He was a great number theorist, and his idea is written as 2 plus 2 power 0. Isn't it? What is 3? 2 plus 2 power 0. 2 is prime number, 2 power 0 is power of 2. If you take 5, how could you write this? Sum of prime and power of 2. 3 plus 2 to the power 1. 3 is prime number and 2 power 1 is power of 2. Is that correct? And if you take 7, 7 is 3 plus 2 squared. 3 is prime number, 2 squared is power of 2. So he saw all these patterns, but unfortunately even Euler knew that 127. So you can keep on extending this up to 125, but the moment you reach the stage 127, you can't write 127 as sum of prime and power of 2. It never happened. And in fact, Euler himself listed some 7 numbers below 1000, including numbers like 127 and 969 in this work, and he knew that such numbers in mathematics history are called obstinate numbers, named after polymath. Such numbers are called obstinate numbers. There are different types of numbers. I had been writing a book called naming numbers, how many types of numbers that are existing. So this is one of such types of numbers, obstinate numbers. So you can't write, so you see that the pattern works right from 3, 5, 7, 11, 9, 11, every odd number it works. The moment you reach 127, it gets small. The moment you reach 969 or several other numbers, the pattern gets big. The next conjecture, Euler was the greatest mathematician of all time. He did great works in all branches of mathematics. And he is even today the most prolific mathematician of all time. His volumes were edited as more than 900 books now. There are more than 900 books in his collected works, and no one could even finish his collected works. He has done almost all branches of mathematics and is considered to be one of great living mathematician at this time. And he, of course, made some errors in his work. So this example that we wanted to just mention to you in a recent talk, making you know that even greatest mathematicians of those times, in some case, slip in their mind of believing that the pattern always exists, but unfortunately, to their belief, it remains right. So unless you have a concrete proof with you, that is how mathematics works. You have concrete proof, you can't believe that the pattern will exist on and on, unless you are very sure about it. And again, these conjectures were not made a simple math. They had deep thought, deep ideas with them. They verified for lakhs, at least lakhs of numbers before making this conjecture. See, for example, if I have a statement and if I just know that it's working for 5 cases or so, I may not announce it as a conjecture. It can never be done. So they made sure that when they announced this conjecture, it works at least for 1 lakh values or 3 lakh values or at least for certain lakhs of values. And even in that cases, well, influential mathematicians who believe that they proved this result, that result. One man claimed that he had a proof of electromagnetic conjecture, that proof came to be wrong. And one man proved that he had proved the Riemann hypothesis. There were more cases, at least each year, one mathematician will come and say that I have proven Riemann hypothesis, but ultimately it gets broken down at some point of time and it remains still an unsolved problem. So I just urge students like you to know about all this important problem, because there are plenty of ideas available. Right, when I say this, but ultimately there is a truth. In our experience, I can very well say that all technological developments and technical advances in sciences basically some way or around depend on mathematics. And I hope that you just know this, all these things with you. There is so much of knowledge available on the internet, you can just go to it and know whatever that is wanted. Read more books and get into deeper passion. Don't just study surface level. Get into deeper way and enjoy study. I thank all the participants here, and I thank Mr. Mahadevan and other volunteers who have given me this golden opportunity to deliver this lecture.
Gave a variety of suggestions, a number of points about different number of types of numbers and all that. And I am now really fascinated with these conjectures that you spoke about, sir. And actually my area of interest is this catalog number he was talking about. I would just like to share one point with all of you, because students, I think you must know there is some application in everything. Mathematics, to learn mathematics, you may be thinking sometimes, where is the application, why do we learn all this? But this nth catalog number actually is used in the field of computer science. I would like to tell you that, especially in analysis of algorithms, we have this nth catalog number defined by 2n Cn divided by n plus 1. That is used to obtain the number of binary search trees. It's actually, if you are going to do by a trial and error method, it's a very, very exhaustive process. Yes, and we have tried this. So this number, this 2n Cn by n plus 1, which is nothing but this nth catalog number that sir was talking about, has a real good application in computer science, and it gives a number of binary search trees, out of which we are able to find out the optimal binary search tree. So that's a very, very important application in computer science. Why I am telling this is, you must know there is an application for everything. Mathematics and computer science, they are totally interrelated, and you must be in a position to appreciate all these things. Thank you, sir. It was a real good speech from you. Thank you.
That is an item in the program, concluding remarks. Normally, the concluding remark will be done by our executive chairman. Today he is out of station. So, I am slightly deviating from the norm. And I would like to call upon any student who has been listening to this lecture to come and give his feedback about this lecture. Anyone, please come. Your concluding remark is eagerly awaited. Come on. Just come and say a few sentences. Bala Vidya Mandir is one of the best schools in the city, and children who have been listening should be able to say something. Come on, quick.
Like the Riemann conjecture and the Catalan conjecture, and it gives us some motivation to think in that way and prove or disprove some of the conjectures, and also